So the next topic is, having done area inside of a polar curve, is to find the area between two polar curves. So I've put up a diagram of what that looks like. Is basically we have some outer curve, which is r, which I've written as r equals f of theta, and we have some inner curve, which is r equals g of theta. And what we want to do is find the yellow region, find the area of the yellow region. In other words, the area that's inside the blue curve but outside the purple curve. You can sort of imagine how you might reason this out. What I might do is say, let's suppose that I found just the area inside the blue curve between, I've written the two boundaries here as theta equals alpha and theta equals beta. And by the way, don't let the Greek letters scare you. Greek letters work the same as Roman letters. So what you imagine you're doing is we're finding the area inside the blue curve between alpha and beta, and then subtracting this striped area which is inside the purple curve. So you might understand that the area of the yellow region is going to equal 1/2 integral from alpha to beta of f of theta squared d theta, where this is the area inside f of theta, and then we subtract from that 1/2 integral from alpha to beta g of theta squared d theta, where this is the area inside the purple curve. In other words, it's the area that corresponds to what I've drawn as the striped region. We can, of course, simplify this a bit because we can simply combine. We have two integrals with the same limits of integration. We're multiplying them by the same factor of 1/2, so that we can simply write this as integral from alpha to beta of f of theta squared minus g of theta squared d theta. So where this is the outer curve and this is the inner curve. Now, where are you going to get confused by this? Let's think back to the early part of the course. We know that in rectangular coordinates, when we did area between curves, we integrated top minus bottom or right minus left. Then when we switched to finding volumes of revolution, that's when we started squaring the curves. So some of you I know are going to look at this and say, wait a minute, I thought when you square each of the curves, that gives us a volume. Well, it depends on the coordinate system. We certainly would not square the curves to find area in a rectangular coordinate system, but hopefully if you've been following and understanding the development of why f of theta squared goes into the integral for area inside polar coordinates, you can see that you do square it when you're finding area in polar coordinates. So just be aware that this looks very much like the formula for volume of revolution by the washer method, but when we're doing this in polar coordinates, this very similar looking formula is actually giving us area between polar curves.